So in the module number 2 of the engineering mechanics creative syllabus, we have the friction. So by definition, the friction, as you all know, when a body moves or tends to move over another body, a force opposing the motion develops at the contact surface. This force, which opposes the movement or tendency of the movement, is called the frictional force or simply friction. Even this friction is the force which help us to walk over the floor. If there is zero friction between the floor and us, we will slip over the floor. The friction is it is due to the resistance to motion offered by minutely projecting particles at the contact surfaces. If a surface is perfectly smooth, the frictional smooth is zero, and there will be temptation for a slipping. The frictional force adjusts itself to the force tending the motion. There are different terminologies coming under friction. First one is the limit friction. There is a limit beyond which the magnitude of frictional force cannot be increased. This limiting maximum value of friction is called as a limiting friction. It is a value of frictional force where the motion is impending. Say you are trying to move a maybe a instrument box over the a wooden platform, right? So on application of a very small force, it will be difficult to slide the box over the wooden platform, but there will be a limiting force or limiting value, or when the force exceeds that limiting friction value, the body will tend to move. So that friction is called as the maximum value of frictional force is called as the limiting friction value. There are two more definitions: static friction and dynamic friction. As you know, one is for the body at rest, and for the second one for the moving objects. When the applied force is less than the limiting friction, so even whatever you apply the force on an object, it is very less compared to the frictional resistance offered. It is limiting friction. Then such a friction produced is known as a static friction, which will resist the movement of the object. When the applied force exceeds the limiting friction, the body will start moving with a force, external force minus limiting friction value. And the frictional resistance experienced while the body is in motion is called as the dynamic friction. And in dynamic friction, it is again classified into two. One, it is the sliding friction, one is the rolling friction. Sliding friction is experienced by a body which slides over the another body. Just like the example of the instrument box over a wooden platform. Rolling friction like the tires over the road. Uh, yeah, coefficient of friction. So this defines the degree of friction value between the body and the platform. Coefficient of friction. The magnitude of limiting friction bears a constant ratio to the normal reaction at the contact surface. That is, limiting friction is proportional to the normal reaction at the contact surface. This ratio or constant proportionality is called as the coefficient of friction. Consider the free body of this body. It will have a weight downward. For this downward force, there will be a reaction force called N, and when the body is tried to move horizontally with a force P, there should be a resisting frictional force. This F is equal to mu times the reaction force, and this mu is the coefficient of friction. For a smooth surface, mu will be 0, hence there is no frictional resistance and the body will simply slide over. And for mu is equal to 1, that is, in that case F will be equal to the N, so it will be equal to the weight of the body, right? So in that case, the friction will be the highest value, and beyond that we can't increase the friction. So mu is equal to F by N, where mu is the coefficient of friction. So in a graphical way, we are increasing the force in static equilibrium to Fm, which is a limiting friction. As a P increases, force increases, the static friction force increases as well as until it reaches a maximum value Fm, which is a limiting friction. Fm is equal to mu s into n, static coefficient, okay, of friction, into n. Further increase in P causes the block to begin to move as F drops to a small kinetic friction force Fk. So upon the start of this object movement, there will be a drop in the friction force, and the Fk is equal to mu k into n, which is still lower than the value, okay, lower than the value of F. The maximum static friction force and kinetic friction force are proportional to normal force, as we know mu into n, where mu is a constant which converts the proportion to a equivalent, like F is actually proportional to n, and this F is equal to mu into n, right? And dependent on the type of condition of corner surface. So definitely, if the I have explained previously instrument box, it depends whether it is located over a steel platform, concrete platform, wood platform. All have different values of friction, and it is independent of the area, contact area, how much area it is uh, contacted. There are some laws of friction. There is the force of friction always acts in a direction opposite to direction of the body moves or tends to move. So suppose the bodies try to move to the right, the friction will be acting in the left direction. Till the limiting value is reached, the magnitude of friction is exactly equal to the force, which tends to move the body. The magnitude of limiting friction, it bears a constant ratio to the normal reaction between contact surfaces, and that ratio we have defined as coefficient of friction. And the force of friction depends on the roughness or smoothness of the surface. So for roughness, friction is 1, smoothness value is 0. The force of friction is independent of the area of contact between two surfaces. After the body starts moving, the static friction will convert into the dynamic friction, and for sliding object, it will be a sliding friction, rolling object, it will be a rolling friction. The magnitude of dynamic friction is less than the limiting friction, and it bears a constant ratio with normal forces. This ratio is called as the coefficient of dynamic friction, which is different from the coefficient of static friction. The coefficient of friction of various surfaces as well as difference between the static and kinetic friction can be illustrated by pulling the objects with spring scale. So it is an experiment to find the friction coefficient. Next, we have the angle of friction. So consider an object, weight acting downwards, reaction upwards. Let's try to pull it. So it is trying to pull the load to the right direction. So hence, obviously, the frictional force will be in the left direction. Okay. So the angle of friction is the angle between normal reaction, that is N, at the contact surface, and the resultant of the normal reaction and the limiting friction. It is denoted by phi. So it is only regarding the resistance of it. Okay. So we know reaction N is equal to W, and F is actually a coefficient of friction times the resistant force. So this is actually moving left, and this is moving, or this is actually offering towards top, and the resultant of this force will act at a particular angle, and the resultant angle with respect to normal is called as the coefficient of, sorry, angle of friction, which is equal to tan inverse of mu. Tan phi is equal to F by N. F is equal to mu into N by N mu. So angle of friction is tan inverse of mu. Next one is for the angle of repose. and it is a maximum inclination of a plane on which the body can repose without applying the external force. So the ideal case is this platform number one, the base one, platform number two. Suppose the platform number two is directly above the platform number one parallelly, then the body will be at rest. When you try to lift the platform 2 at an angle with the platform 1, at a particular angle alpha, the body will simply slide over. So that angle which makes the body unstable, or which makes the body to move without applying any force externally, is called as the angle of repose. And these are the various forces acting on that particular condition. The weight will always acting downwards, W, and this angle of repose alpha will be equal to the angle alpha with respect to the perpendicular to this platform. So this alpha, so this component is W cos alpha, and this is W sin alpha. W cos alpha, as this is downwards acting down, and this is this one in taking resolving it, so horizontally W sin alpha tends to move the object to the bottom, and there will be a n force which is directly perpendicular to the platform. F is equal to mu1 is always resisting the motion, as the body will definitely slide down as we are not applying an external force. The frictional force is actually moving up. So these are explained here. Consider a block of weight W resting on an inclined plane which makes an angle alpha with the horizontal. When alpha is small, the block rests on the plane. Obviously, if the alpha is increased at a particular alpha value, the block will start sliding down, and at a particular stage, this motion impedance F is will be equal to the mu n. So it's about resolving the forces. So we have can resolve this into both axes, taking one parallel to the platform 2, this one inclined surface and vertical one. So the parallel to this one we have F is equal to mu1 and W sin alpha. So mu1 minus W and sin alpha both are acting reverse direction, because this is opposing, this is the force to move the object is equal to 0, mu1 is equal to W sin alpha. In perpendicular, we have reaction minus W cos alpha and equal to W cos alpha. So we have equating that mu into n, we have W cos alpha. Mu into W cos alpha is equal to W sin alpha. So this W will get cancelled, and mu is equal to sine by cos, which is tan alpha. So alpha is equal to 5. So here we are concluding that the angle of repose is equal to the angle of friction. So in the problems, if the angle of friction is given, directly you can, it's indication of the value of angle of repose, both are same. Next term is the cone of friction. Consider the limiting equilibrium of a body kept on a horizontal surface. Let P be the applied force and N be the normal reaction. We have the body here, weight applying downwards, reaction N. P is the force which pushes, and we know F is equal to mu1 is the resisting frictional force, and R is the resultant force. With respect to normal, it is like the angle of internal friction phi. So we have F is equal to mu1. The resultant of limiting friction and normal reaction makes an equal to angle of friction with normal reaction. When the direction of force is changed, the direction of resultant changes, but the angle between the N and R will be the same. Okay, so for this condition, the resultant of limiting friction is F is equal to mu1, and the normal reaction, the resultant is actually R. Makes an equal angle to angle of friction with normal reaction. So that angle will be same. when the direction of force is changed, that is, we are applying the force in this direction, right? Suppose we are removing this P and applying from like right to left. The only thing is that the angle will just shift to this point. The other thing is that the new direction will be this, and this is called as the cone of friction, provided the both the phi will be same. Phi and phi will be same, only the direction changes, which is called as the cone. Pointer pink color I'm taking as a green. So this will be the cone of friction. Yeah, this is the demonstration of that. So for a 360-degree, it will be like a cone. When we are actually revolving this one with respect to the vertical axis, we will get into a cone, which is called as a friction cone or the cone of friction. This axis of the cone will be normal to the reaction. Generators of are the resultant of force R, and the base of radius equal to the limiting frictional force. There are four situations can occur when a rigid body is in contact with the horizontal surface. One is like this. In this case, the weight of the body is in four cases it is downward, and in first case no friction. That is, assume that the surface is very smooth, so that on application of the weight, already weight is there. When you apply P also, P plus W will be the net force downward, and reaction will be equal to P plus W. There is no horizontal effect. This force is also vertical. There is no inclined surface. So there is no cosine terms comes into picture. When there is no motion, but there is some friction value. It is within the static friction. And see that we have the weight and reaction, and this F horizontal friction is will be equal to Px. That is, if the force is acting in an inclined way, the four situations can occur: rigid body in contact with the mm, yeah. Actually, this is in what I'm telling is that this body is not in motion, so the friction force is not in action right now, right? Only the static friction is there. So when there is an inclined force P which tries to move the object, the cos component or the Px component will be equal to the F value, and when the Px exceeds the F value, the body will tends to move, and F in this case will be less than μs into n, as it is not in motion. Μs is a static friction, and n is equal to weight plus y component, the component of the P, no motion. Okay, Ps is less than F. Okay, motion impending, that is starting as a limiting friction value. Here Fm is equal to Px, that is the horizontal force is equal to the frictional limiting force. Fm is Px, Fm is equal to μs into n, and n is equal to Py plus W. Okay, and in motion we know that the Fk kinetic friction, we have Fk is less than P, that is resisting force Fk is very less than the actual force on the body, and Fk is equal to mu k into n, where k is the kinematic friction and n is equal to Py plus W. So these are the four conditions when the body is at rest, and there is surface smooth. Second one, the motion is not started. Third one, limiting friction or the motion is going to start, and the fourth condition is the body starts moving. Another same similar way, we have an inclined surface. So by default, the surface is actually promoting the body to move down, right? Or it's encouraging the body to move down. In first case of horizontal platform, no friction, W is equal to R. So we are not applying any external force here. Okay. So another one is second one is no motion. That is motion impending, and the fourth one is motion. Okay, so the that external force will be coming or will be derived from the weight as it is on an inclined surface. So we have W here. Theta is the angle of repose. W sine theta is the horizontal force which tries to slide down the object. W cos theta, sorry, W sine cos theta is the force which is perpendicular to the platform, and W sine theta will force the body to slide down. So in that case, we have the and reaction is equal to W cos theta directly, and F is equal to W sine theta. Now motion. In case of motion impending, we have N is equal to W cos theta, Fm is equal to W sine theta. In this case, theta is equal to phi is equal to angle of repose. And third one, that theta inclination of this platform is greater than the angle of repose, so that the body will move down. A simple problem: a body of weight 1000 Newton is kept on a static, horizontal rough surface. Coefficient of static friction is zero point 0.2. Is mu. Coefficient of dynamic friction is 0.18. Calculate the frictional force when the applied force is as shown below. P is changing from 0, 100, 200, 300. Weight is 100. Okay. So it's telling that rough surface, static coefficient zero point 0.2, dynamic 0.18. So we can do the problem. P equal to 0. P equal to 0 means the body, we are not applying any force. Hence, the weight will be equal to the reaction. So there won't be any frictional force. 0. You are asked to find the frictional force. P is equal to 100. So we know mu is equal to F by Rn. F is equal to mu into Rn. So zero point 0.2 into 1000. The reaction is 200. So the applied force is less than the resisting force, resisting frictional force 200. So the what I really said that the frictional force is strong or is more compared to the acting force. So on application of 100 Newton, the frictional force will be 100. Okay, when you apply 200, it will be equal to the frictional force, and when the P is more than 200, the body will start moving. It is the subsequent step. 200, that is the motion impends, starting force, and P 300, the P is actually 100 more than the frictional force. But there is a change in that. That is, once the body starts moving, the frictional force or the coefficient of friction will decrease. So the zero point 0.2 will change to 0.18. So 0.18 to 300, 180 will be only the resistant frictional force during the dynamic motion. So 300 minus that okay, sorry. So the frictional force applied will be only maximum 180. The applied force is 300. So even if that value is increased, the frictional force can offer only maximum of 180 Newton. Please think that if you want to make it non-moving, then another option is that you have to put some weight over the body so that this frictional force is increased from 1000 to a higher value. Right, if you even double or same one more object is placed on that, but that depends because that between that newly placed body also there should not be any friction. If it is tightly placed, then you can increase the frictional force. We will see that later. A body of weight 300 Newton is lying on a rough horizontal plane, having a coefficient of friction zero point 0.3, magnitude of force, which can move the body while acting at an angle of 25 degrees with the horizontal. So you have the figure like this, and the object weight is 300 Newton. Uh, so the reaction is actually moving up R, and the force applied at an angle of 25 degree. and this is frictional force. So we are given value weight 300, coefficient of friction zero point 0.3, angle made by the force 25. So this force can be resolved in horizontal and vertical. This cos 25 is the force which pulls the object, which is this value P into 0.9063. On vertically resolving it, reaction R is equal to W minus, because this angle will convert upon resolving. Yeah, so this will be adding or in different direction to the weight, so that's why W minus P sine alpha, this one is P sine alpha, is equal to this is the value obtained. So we know that for the force of friction, that is 0.9063 p is equal to mu into r. The limiting friction is equal to zero point 0.3 into this much value, and upon that we can find the force required to initiate the movement of the object, which is asked in the question. The force required to move the object. These are the repetition problems. The body uh, resting on a rough horizontal plane required a pull of 180 Newton in the incline at 30 degree. The plane just to move it. It was found that a push of 220 Newton inclined at 30 degree to the plane just move the body. Determine uh, that the weight of the body and the coefficient of friction. So that question is a body resting on a rough horizontal plane. So there is a coefficient of friction, horizontal plane, required a pull of 180 Newton inclined at 30 degree to the plane just to move it. So this force has to be resolved in the horizontal direction to find the limiting frictional value. It was found that a push of 220 Newton in the same inclination, it actually moved the body. Okay, determine the weight of the body and the coefficient of friction. So it's actually a kind of back calculation. So given pull 180. Uh, okay. So one more thing to note is that the 180 is actually a pull and 220 is actually a push. That's the main difference, which has to be you should be alert in this question. Given pull is equal to 180 Newton, push is 220 Newton. Both are acting at same angle, alpha 30. W weight of body, R normal reaction, mu coefficient of friction. First of all, consider the pull of 180 Newton acting on the body. So resolving that, 180 cos 30 will be the pull. 180 cos 30 is equal to 180 into 0.866. This 0.866, um, yeah. So this is actually F1 value. Cos 30 is 0.866, 155.9. Resolving in vertical, R1 reaction is equal to W minus, in the previous problem, like that this reaction will be having a upward resolution. So that W minus 180 sine 30, W minus 90 Newton. So one more thing we know that the for the calculation of force of friction is equal to mu into R1. Right, so frictional force 155.9 is equal to mu into R1. So R1 we got it as W minus 90. So here unknown thing is W and mu. So we have one equation, two unknowns now. So we need one more equation uh, to solve the two unknowns. Okay, so the second equation is formulated based on the 220 push, and so that the first equation and second equation have the mu and W in common, so that we can work with that equations to solve for the two unknowns. So now consider a push of 1 to 20 Newton acting on the body. We know that in this case, the force of friction F2 will act towards right as shown in figure 8.3b. Resolving the forces horizontally, F2 is equal to like the previous one. Only thing is that the changes in angle. That is, please note that 180 cos 30 will be uh, towards right. It is actually a pull, right? This 220 cos 30 will be a push. This acting towards a left. So that horizontal things will change. One more thing is that the this component in the vertical direction will be opposite direction to the weight. Here it will add on to the weight. So that's why F2 is equal to 220 cos 30. We got the value. R2 is actually plus because of similar direction action. And on substitution, okay, we got second equation. Then you can directly solve the two equations. There are two unknowns, and you can find the W. So what we have done here done is that they have divided the equation one, this equation with the equation two, so that left will be a like a value and is equal to mu will get cancelled, W minus 90 by W plus 110. Upon solving, you will get W as 991.2. Then applying to any equation 1 or 2 to find the mu value. A block weighing 500 Newton just starts to move down a roughly inclined plane when supported by a force of 200 Newton acting parallel to the plane in upward direction. A block weighing 500 Newton. So weight is given here. It's a rough surface and trying to move by 200 Newton acting parallel to the plane in the upward direction. Try to pull the load. Okay. The same block is on the verge of moving up the plane when pulled by a force of 300 Newton. So the question is, a block weighing 500 Newton just starts moving down a rough inclined plane when supported by a force 200 acting. So when you're trying to lift by 200, the body will try to slide down. The same block is on the verge of moving up. So we are giving additional increasing 100 more load. It is trying to move up. Find the inclination of the plane and the coefficient of friction between the inclined plane and the block for this corresponding case. First, the question is clear to you, right? This weight is there. On application of 200, the body will move down. On applying 300, the body will try to move up. So the 300 is the minimum required force to pull the object upwards. So you are supposed to find the theta for this corresponding condition. So we have the free body diagram of the block when it just start moving down is shown in 5.7a. Direction of the frictional force is upward in the case since direction is impending motion towards downward since limiting case. So F by n is equal to mu known to you. For the force perpendicular to the plane, so perpendicular to the plane we have the 500 cos theta downwards is equal to reaction. So n is equal to 500 cos theta and also F1 is equal to mu into n. So 500 mu cos theta is the frictional force. For the forces parallel to the plane, we have this component of 500 which will try to push the body down and 200 to lift, right? 200 lifting positively, um, then force is friction force is resisting the downward motion and minus 500 sine theta is actually adding or the weight component which tries to pull down the object. So you got an expression like this. Similarly, for the condition, just for 200 Newton, condition of 300, you have again resolving this. The n is equal to 500 cos theta, f2 is equal to 500 cos theta. Then this is the changing value. Force parallel to the plane. Instead of 200, now it's changed to 300 minus F2 minus. So there is an important thing. That is, on application of 200 Newton, it was told that the body is trying to move down. So in that case, the frictional force should be towards up direction. Okay. On the application of 300 Newton, the body is starting to move up, so that the friction F2 should be in the downward direction. That's the main thing. That's why compared to the previous one, here plus F1, here actually is a minus F2. Other things are same, and by solving the equation 1 and 2, we will get the theta is equal to 30 degree. And then you can apply in any of the equation to find the mu value. Okay, a different problem which have two objects and a pull is there. What is the value of the P in the system shown in figure 5a to cause the motion of 500 Newton block to the right side? Assume the pull is smooth and the coefficient of friction between the other contact surfaces is 0.20. So you have a what is the value of P in the system? P is unknown. To cause the motion of the 500 Newton block to the right side. So this P should try to move the 500 Newton right side. Assuming the pull is smooth, there is no friction loss at this point, and coefficient of friction between the other contact surfaces is 0.20. So this is 0.20, this is 0.20. So what is the value required by P to just initiate the movement for this condition? It's about resolving the forces for differently for free body diagram for F750 and for the 500. So let's start from the free end, having very less forces acting. For this 750, as you know, 750 weight acting vertically down, 750, this inclination will be equal to this inclination of the body, 60. So you have the component 750, 60. Then there will be a sine component also, and the reaction will be there, right? So the sine component is actually pushing the hmm, the sine component is actually pushing the object or the body downwards. But in our entire question, we are trying to lift it up. So we are assuming that the body starts moving upwards, so that the friction is taken in the reverse way. Okay, this F1 is dependent on the uh, total problem. Right, this we are assuming that the 750 Newton weight is moving upwards, so that F1 is in negative direction. So that normal to the plane, we have the N1 reaction on 750 is equal to 750 cos 60. So N1 is 375. Since the motion is impending, F1 is equal to mu into N1. So 75 is the frictional force maximum offered in an impending condition, and for the forces parallelly, we have the tension force on the string T minus F1, as we told, minus F1 minus 750 sine 60. This component of this one will be, yeah, in the downward direction, sine component. So you got the value as 724.52. And now we are taking this tension alone to the second FBD. Tension here it is in the right direction, taking here in the negative direction for the continuity. So the consider the equilibrium of 500 Newton block. Sigma b is equal to 0. So we have a force also coming here, right? So this force is actually unknown to you. So sigma b is equal to 0. That is N2 reaction 500 downwards plus P sine 30. So this component the is actually sorry, yeah, so pointer pen. This will having a component like this and this, right? This is actually parallel to this T. Okay, so this is actually sine and cos. So the pin sine 30 will be acting in direction of N2. So N2 we got as this value, and from loss of friction F2 is equal to zero point 0.2 into N2 is equal to 100. That is zero point 0.2 into. Uh, so this is actually substituting the N2 value which we got from the previous equation. So 100 minus zero point 0.1 NP. Sigma H equal to 0. We have the cos component, this one, tension component, then the friction component. On substitution, we have T and F2 in left direction, and the force P cos 30 right direction. Substitution, we get the P value as 853.52. So the last type in this video, this will discuss on the connected bodies. In this one, we have two objects coming in the calculation, and for that, the block A, here block A weighing 1000 Newton rest over block B which weighs 2000 Newton as shown in figure. Okay, the figure is clear to you. The block A is tied to the wall. The block A is this one tied to the wall with a horizontal string. If the coefficient of friction between the blocks A and B, this is the friction between A and B, 0.25. Between B and floor is one third or 1 by 3, 0.333 between B and floor. What should be the value of P to move the block B if P is horizontal? P is horizontal, P acting 30 degree with the horizontal. So you want to solve from A to B, right? Because A is having the minimum forces. So FBD of the A first. Considering the block A, we have drawn here. This is actually block A. 1000 Newton is its weight downward. Tension, because there is a string attached, tension. Reaction is N1 for A, and there will be a frictional force. And for 2000 also, we have vertical force, weight, then N2 upward, then P horizontal. Then you should have due consideration on selecting the frictional force. That is, uh, imagine that we are applying the force on B. We are applying force on B. So think when you try to move the body B to the right, there will be a tendency for the A also to move with the B, right? Uh, just a minute. Yeah. So considering the body A, sigma B is equal to 0. Weight acting downwards 1000 and reaction force we have N1. So 1000 is equal to the N1 value. Okay. And F1 is the limiting friction. F1 by N1 we have is equal to mu is equal to 0.25. So if the question is given that between A and B the value is 0.25. So this 0.25 is known to you. You can find the F1 value as 2250 Newton. So here the tension is offered by this string is acting left, so that there will be a resisting force right for the body to be in equilibrium. So we have the F1 in the right direction. So when on contact surfaces, if F1 is in the right direction, immediate the next surface, the F1 should be in the reverse direction. Okay, so that both will be incompatible. It will be incompatible condition. So the sigma h equal to 0, F1 minus t, F1 minus t for the object A, at t is equal to 250 Newton. So this will be in the total equilibrium. Consider equilibrium of block P, sigma v is equal to 0. We have N2, N2 is actually acting upwards. On N2 there will be weight of object 1 and 2. 1000 plus 200 will be the total weight. So N2 is equal to 3000 Newton. This I was previously explaining, like to make the object safe, you can place one more object above the uh, reference or the considered object, but there is a friction between the two objects happening, which has to be calculated. So F2 by N2 is equal to 1 by 3 is given here between the objects, and F2 is equal to zero point 0.3 into N2 is 1000 Newton, and we have P is equal to, so when there is a right force, the opposing force will be towards left. So F1 F2 is in the same direction. F1 plus F2 is equal to P. We know the value of F2 from the equilibrium of block B and F1 from the equilibrium of block A. Adding, we get 1250 Newton. When the P is inclined, the final case, P is inclined. In that case, only that resolution of forces will change. All others will be remaining same. Sigma b is equal to 0. Yeah. So as it's inclined, then additional force P will be resolved in vertical horizontal direction, which keeps up changes in forces. So N2 is the reaction force, um, will be equal to obviously the weight of object 1 A and B. 2000 plus the 1000 is already there, plus this P component sine 30 is upward. It's actually releasing the N2. So N2 is equal to 300 minus zero point 0.5 into P. From the loss of friction, we have F1 plus F2. Then P cos 30, right? So F1, so F2 value will change. So it is 1 by third of N2. It is 100,000 minus zero point 0.5 into P by 3. And sigma h equal to 0, we have P cos 30 is equal to F1 plus F2. On solving, we will get as P is equal to 1210. That implies that you need lesser forces, 1210 is the inclined force, and 1250 is the horizontal force. So uh, you need more force in the parallel direction compared to an inclined force. But even if the inclination is more, then the changes will happen in the value, right? And one more problem, what should be the value of theta, this theta value? In figure 5.6a, that will make the motion of the 900 Newton block down parallel down to the plane to impede the coefficient of friction of all contacts 1 by 3. Between body 1 by 3, between body and surface also 1 by 3. So consider only the 300 first. So we have a string attached, right? So consider the equilibrium of a 300 Newton block. Sigma forces normal to the plane equal to 0 gives, for this one we have the weight inclined downward, then upward. So n1 is equal to 300 cos theta, will give you as 300 cos theta. We have to find the theta value, right? So n1 is like this. from the loss of friction, F1 is equal to one third of N1, which is 100 cos theta. Then, considering the uh, equation of 900 block, again we have N2 upward, N1 upward. So N2, sorry, the N2 is the final reaction, right? So upon N2, there will be the weight of object 300 Newton and 900 Newton. So 300 Newton weight perpendicular to this plane is N1. So N2 minus N1 minus 900 cos theta equal to 0. So N2 is equal to N1 plus 900 cos theta, which will give you 1200 cos theta. Similarly, F2 is equal to one third of N2 is equal to one third of 1200 cos theta is equal to 400 cos theta. So since the forces are parallel to the plane equal to 0 condition, we will get that the F1 plus F2, F1 plus F2 is equal to this 900 sine theta. On solving the value, we get theta is equal to 29.05 degree. That's the end of this video.